Now, another important topic, which is nothing but complements, friends. This topic is very important, friends. So let us see this. See, complements have two types of complements, friends. Radix complements and diminished radix complements. Radix complements are denoted by R. Diminished radix complement are represented by are denoted by R minus 1. Fine. What do you mean by R's complement, friends? Here, let us assume a number of base R has n number of digits in integer part and m number of digits in fractional part. Let us suppose that. Then R's complement is nothing but r power n minus n for all if the number is not equal to 0 and 0 for all n equals to 0. Fine. R minus 1's complement in the sense is nothing but r power n minus r power minus m minus capital N. Here this n is nothing but the number. This is nothing but the base, this is nothing but number of digits in the integer part, and this is nothing but number of digits in the fraction part. If we apply this formula, then we will be getting the complements format. Let us solve few problems, then you will understand how to apply these formulas. Let's see. Okay, now friends, let's solve this question. Find 10's complement and 9's complement of 0030700 of base 10. He is giving base 10. That means we have to calculate 10's complement and 9's complement. So generally the R's complement is r power n minus the number, right? So this is the formula we have obtained. So now how can we calculate 10's complement, friends? 10 power 7 is nothing but 0, 0, 0, 0, 0, 0. Yes or no? Minus we have to do 0, 0, 3, 0, 7, 0. Yes? Now calculate. There are two zeros, so we have to take borrow here. 0, this is 9, this is 9, this is 9, this is 9, and this is 10. Right? So 10 minus 7 is nothing but 3. Yes or no? 10 minus 7 is nothing but 3. This is 9, this is 6, this is 9, this is 9. So this is the 10's complement of the given number. Now let us see the 9's complement. 9's complement formula is nothing but diminished radix complement, right? This is r minus 1. This is r and this is r minus 1. So r power n minus r power minus m minus number. So this 10 power 0, 10 power 7 is nothing but 1, 2, 4, 5, 6, 7. 10 power minus 0 is nothing but 10 power 0. There is nothing but 1, right? So this is minus 1. Before that, let us go for 10 power 7 and this value is 1. 1 minus 0, 0, 3, 0, 7, 0. This value is nothing but if these two will get added, right? So what will be this value? Minus 0, 0, 3, 0, 7, 0, 1. Yes or no? If these two will get added, so 7, 0, 1. Okay. Now these two will get subtracted. Now we will be getting 3, 4, 5, 6, 7 minus 0, 0, 3, 0, 7, 0, 1. So what we will get, friends? So here 0, 9, 9, 9, 9, 9, 9 and it's 10. 10 minus 1 is nothing but 9. Yes or no? 10 minus 1 is nothing but 9, right? Yes. 9 minus 0 is 9 and 9 minus 7 is 2. 9 minus 0 is 9. 9 minus 3 is 6. 9 minus 0 is 9. 9 minus 0 is 9. So this is the 9's complement. That is 99692999. So this is the way how we obtain 10's complement and 9's complement for a given number, right? Next one. Now friends, let us see a small shortcut to obtain complements, friends. No need of applying those two formulas. See, listen. To get R's complement of a number in base R, leave least significant zeros. Leave least significant zeros means which is the right hand side, the last zeros as it is, and subtract the first non-zero least significant digit from R and subtract the remaining digits from R minus 1. Okay, first non-zero from right side position, subtract first non-zero from R and the remaining digits from base minus 1 to obtain R's complement, friends. And second one is to get R minus 1's complement of a number in base R, subtract each digit from R minus 1, friends. Hope you understand. Basing on this, let us do two problems basing on these two formulas, these two shortcuts. Now then you will be understanding much more. So take this example, friends. Here the number is 00307.20600, which is of base 8. We have to find 8 and 7's complement. So see how we have to do to get R's complement. R is nothing but 8 here and diminished radix complement R minus 1 is 7 here. So find first R's complement. What he is saying, to get R's complement of a number in base R, leave least significant zeros as it is. See suppose this is the question, right? This is the least significant bit and this is the most significant bit. This is called the LSB and this is called MSB. Fine. So if what he is saying, that he is telling us to leave the least significant zeros as it is. So these are the zeros, we are keeping it as it is, right? So what he said, subtract first non-zero least significant digit. First non-zero least significant digit is nothing but 6, right? So it should be subtracted from base R, that is nothing but 8. This is called 8th complement. 8th complement. This is 8th complement. So 8 minus 6 is nothing but 2, right? Yes, 8 minus 6 is nothing but 2. So, and we have subtracted, and subtract remaining digits each from R minus 1. Subtract each remaining digit from 7. Right? This is R minus 1. Leaving the least significant digits as it is, subtracting the first non-zero digit from R and subtracting every other digit from R minus 1. So what we will get? 7 minus 0 is 7, 7 minus 2 is 5, 7 minus 7 is 0, 7 minus 0 is 7, right? Next 7 minus 3 is 4, 7 minus 0 is 7, 7 minus 0 is 7. This is what? 8th complement for this particular number. Okay friends? Now let us see the 7th complement. 7th complement. So what he is telling us, to get R minus 1 complement of a number in base R, subtract each digit from R minus 1. In the sense, so this is the number 00307 and 0.20600. Yes. So no need of thinking of least significant zeros, whether to leave it or not. Subtract every digit from R minus 1, R minus 1. So subtract every digit from 7. That's all. So what is the value that we are going to get? 7 minus 0 is 7, 7 minus 0 is 7, 7 minus 6 is 1, 7, 5, 0, 7, 4, 7, 7. So this is the 7th complement, friends, right? I hope you understand. What my point? So 8th complement is this and 7th complement is that one. In the same way, we can perform 2's complement and 1's complement also. First, let us see that. So let us find 2's complement and 1's complement for this number, friends. That is 0101001 minus 0.10100, right? So 2's complement is, how to find 2's complement? Is nothing but first we have to leave the least significant zeros and subtract the first non-zero digit from the least significant digit from R and subtract the remaining digits from R minus 1. Okay, see 2's complement here in the sense 0 1, see 0101001.10100. So I have to leave the least significant digits like this. Subtract this from 2 and remaining from 1. That's what he is saying. Yes or no? So 2 minus 1 is 1. 1 minus 0 is 1. Next 1 minus 1 is 0. 1 minus 1 is 0. 1 1 0 1 0 1. Right? Is this the 2's complement, friends? Now, in this way we can solve. There is also another shortcut, very important shortcut and very easy shortcut in order to find the 2's complement, friends. Let us see that. See. So, what he has given, another shortcut. This is the important shortcut, friends. 0101.10100, right? See, listen carefully. Go from this side. Go from right to left. While you are going, search for the first non-zero number, that is nothing but 1. Until you get 1, you go on writing the same digits. Yes, this is the one here, right? First you write the digit 1 and from that, if it is 0, write 1 from first non-zero number, stop. If it is 0, take it as 1. If it is 1, take it as 0. Take alternate numbers. So firstly we have 0. Take the 0. We have 0. Take that 0. Yes, we have got the first non-zero number. Take that. And from that, what we have to do? We have to invert all the digits. That is nothing but 0 as 1, 1 as 0, 1 as 0, 0 as 1, 1, 0, 1, 0, 1. So this is the 2's complement. Right, friends? Same, right? 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 00. Yes or no? So what you have to do is, until you get first non-zero number, until that you have to repeat that first non-zero number, also take that. After that you invert the digits, right? This is also one of the simple shortcut to find 2's complement. Now let us find 1's complement. See, 1's complement, what he is saying, to get R minus 1's complement of a number in base R, subtract each digit from R minus 1. That is nothing but simple, friends. 1's complement here is simply invert all the digits. 1 minus 0, 1, 1 minus 0, 1. 2 minus r is nothing but 2 here, right? 2 minus 1 is 1, right? So we have to subtract every digit from 1. When we are subtracting every digit from 1, these digits will get inverted. That means the ones complement for 0, 1, 0, 1, 0, 0, 1.10100 is 1, 0, 10110.01011. That's all. Invert every digit. If it is 0, take it as 1. If it is 1, take it as 0. That is nothing but ones complement. Hope you understand. Take these two shortcuts. So next concept, friends, representation of signed numbers. So before going to see this representation of signed numbers, we will be discussing about three things. First thing is sign magnitude, second one is complements in two different type of complement methods. Let us see those. First one is signed magnitude representation. Signed magnitude representation. There are totally three types of representations, friends. First thing is called signed magnitude representation. Here we will be discussing about a number with its sign and its magnitude. How we are going to discuss this representation? Let us see that. Come on. Okay. See here in sign magnitude representation. In sign magnitude representation, MSB is used explicitly. That means separately we will be having special significance on MSB, friends. For sign, MSB used explicitly only for sign. That means the MSB bit, the most significant bit, is used only to represent the sign of the number. Okay, which does not having any magnitude, and this MSB bit does not having any magnitude. It does not says about magnitude, says about only sign. And the remaining bits are used for magnitude. Okay, see friends, suppose I have some digits. In that digits, n digits are there. The MSB digit represents sign, and the remaining n minus 1 digits will be represented as magnitude. Okay, if MSB is equal to 0, if this MSB bit is equal to 0, the number is positive, and if MSB is equals to 1, the number is negative. Okay friends, see for example, here 0, 0, 0, 0. These three represents magnitude of the number, and this is the MSB, right? This is the LSB and this is the MSB. Okay, the MSB represents what? Sign, right? So 0 is there. If MSB is 0, the number is positive, right? So plus 0. If the MSB is 1, number is negative. So minus these three is nothing but 0. So this is 0, 0, 0, 1. That is nothing but 0 means plus, 0, 0, 1 means 1. Next here, this value is nothing but 41, friends. If you calculate 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5. That is nothing but 32, 16, 8, 4, 2, 1, right? So 32 plus 8, 40, 40 plus 1, 41, okay? So, okay. So plus 41, and this is, here this is MSB bit, this represents sign, that is minus, and the same digits are there, minus 41. So in this way we used to represent numbers in sign magnitude representation, but carefully look at this. There is a one main drawback, friends. What is that? Here plus 0 and minus 0 is there. This is the main drawback, means 0 is represented by 2 times. This is the main drawback. This is the drawback. 0 is represented in 2 formats. See, one format is sufficient, right? If we are getting 2 formats, size increases. It takes the memory, much more memory, right? So this type of representation has such a drawback, which is nothing but it will be having 2 places to represent, two representations for 0. Hence, this is the main drawback in this representation. Therefore, we will be going to ones complement. And at the same time, the range of n bits in this sign magnitude representation is, remember this formula, minus of 2 power n minus 1 minus 1 to plus of 2 power n minus 1 minus 1. That means if there are 4 bits, friends, suppose. So what is the range from where to where we can represent from? If suppose range of 4 bit is minus of 2 power 4 minus 1 is nothing but 2 cube, that is 8. 8 minus 1, 7. From minus 1 to, so 2 power 4 minus 1 is 2 cube minus 8 is 7 plus 7. From minus 7 to plus 7, we can represent the numbers of 4 bits in this sign magnitude representation. Okay friends, remember this formula. Now let us go to ones complement representation. Now next concept, friends, ones complement representation. The general format of ones complement representation is minus of 2 power n minus 1 minus 1, 2 power n minus 2, 2 power n minus 3, and so on, 2 power 1 and 2 power 0. See friends, carefully, only the MSB bit is having only the negative term, that's all. remaining all the n minus 1 digits are in positive terms only, but only the MSB bit is only negative term. Remember that. Okay, fine. If the number is positive, the magnitude is represented in its true binary form. Fine. If the number is positive, magnitude is represented in its true binary form. And what about the sign bit then? Then the sign bit B is 0 be placed in front of MSB. Right? Next one. If the number is negative, suppose if the number is negative, the magnitude is represented in its ones complement form. If the number is positive, the magnitude is represented in true binary form. If the number is negative, the magnitude is represented in its ones complement form. And what about the sign bit here? Sign bit 1 is placed in front of the MSB. Remember that. If the number is positive, true binary form, and the sign bit is 0. And if the number is negative, the magnitude will be ones complement form and the sign bit is 1 placed in front of MSB. Suppose, for example, look at these questions, friends. Suppose 0, 0, 0, 0. Suppose we want to represent plus 0 in ones complement method. See, friends, plus 0 in the sense these 3 is nothing but zeros, right? The number is positive, so put 0 and write its true binary form, that is 3 zeros. If I want to represent plus 1 in ones complement representation, see friends, plus 1 is asking, so it's a positive number. So what is the magnitude of 1 in the true binary form? 0, 0, 1. So plus, that's why you have to keep positive, 0, right? Next, how can we represent plus 5 in ones complement representation? It is a positive number. So represent 5 in true binary form, that is nothing but 1, 0, 1 and put 0 in front of MSB, right? Next one, how can we represent plus 7 in ones complement form? So 7, this is a positive number, so we have to do it in a true binary form and put 0 in place of MSB. So true binary form is nothing but 111 and the MSB is nothing but 0. Right or not? Now see, let us think about the second line, which is representing the negative numbers. See, if suppose I want to represent minus 7 in terms of ones complement representation. So since the number is negative, I have to take ones complement of the true number. What is the ones complement of 7, friends? I have already told you. 7 is nothing but 111, right? What is the ones complement of 111? It's nothing but 0, 0, 0. Simply inverting the digits. So I have to take these 3 zeros. I have to keep place because of negative number. We have to place 1 in front of MSB, right, friends? Now, how can I represent minus 6? Since this number is negative number, I have to take the ones complement of this magnitude. What is 6, friends? 6 is nothing but 110 in true binary form. What is the ones complement of 110? 100. This is the ones complement. So 001, and we have to, since it is a negative number, we have to keep 1 in front of MSB, right? Now, how can we represent minus 3 in ones complement representation? The binary form of 3 is 011 and the one complement is 100. So 100, since it is negative number, I am keeping 1 here in front of MSB. And even see, here comes the logic. If I want to represent minus 0, so 0 in its, since minus 0 is negative number, I have to write ones complement representation for 000 is nothing but 111. Yes, 111. Since it is negative number, I will be keeping 1 in front of MSB. Here also, as we seen in the sign magnitude representation, here also plus 0 and minus 0. Two representations are there for 10 number. Generally 0 is 0 itself, right? But here in this representation, we are getting plus 0 and minus 0. Thus, memory increases, size also increases for the bits. So for this case, this is also drawback in ones complement representation. So the main drawback of sign magnitude representation and ones complement representation is we are getting two times zeros. Okay. So here see, in ones complement representation, the only bit in MSB has negative weight. We have seen here in the general format. This particular MSB is only having negative weight, and remaining n-1 digits are not having negative weights. Right. Next. And the remaining bits are positive weights only. Fine. The range is minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. Same as sign magnitude representation range. Right, friends? Remember this formula. This is very important. We will be using this formula in our questions, in our previous gate questions while we are solving. Now, let us go for 2's complement representation. So now let us see the 2's complement representation, friends. See, the general format is minus of 2 power n minus 1, 2 power n minus 2, 2 power n minus 3 and so on, 2 power 1, 0. In ones complement form, there is minus 1 here. 2 power n minus 1 minus 1 here, but in 2's complement form there is only 2 power n minus 1. That is the difference. Here this is the MSB, and MSB is the only negative term and the remaining all the terms are positive terms, right? So if the given numbers is positive, the given number is positive, the magnitude is represented in its true binary form and sign bit 0 is placed in front of the MSB. Same as 1's complement form, friends. Okay, here. Now here the statement changes. If the given number is negative, the magnitude is represented in its 2's complement form and a sign bit 1 is placed in front of the MSB. There it will be represented in 1's complement form. Here it will be represented in 2's complement form. That's all. Everything is same. So we already know that 2's complement is nothing but if we can add 1 to 1's complement form, it gives 2's complement form, friends. That means 1's complement plus 1 is nothing but 2's complement. Okay, fine. So let us see a few examples. 1,000 is minus 8. That means here, remember friends, here what he is saying 2 power n minus 1, right? So how can I write in the sense? See, 2 power 0, 2 power 1, 2 square, this is minus 2 cube. This is the format of what? 2's complement. In 1's complement, the format will be 2 power 0, 2 power 1, 2 square minus of 2 cube minus 1. This is the 1's complement representation. Right? 2's complement representation will be in this way. Fine. So, we will be following. Look at the board. This is nothing but 0, 0. Minus 2 cube in the sense minus 8 only, right? Yes or no? No. See, this is 2 power 0, 2 power 1, 2 square. This is minus 2 cube. So, minus 2 cube in the sense minus 8 plus 1. That is nothing but minus 7. So, in this way, minus 7 is represented in we can also use this shortcut to represent in any number, either positive number or negative number in 2's complement. But see here, according to definitions, 8, this is minus 8 he is given. Negative number in the sense, what we have to do? We have to obtain 2's complement of the number and a sign bit 1 is placed here. So, here, this is exceptional case. From here, look at the board. 7, negative 7 he is asking. Minus 7 in the sense, since the number is negative, we have to obtain 7. What is the value of 7, friends? 111, right? What is the 2's complement of 111? 1, 0, 0. Yes or no? 1, 0, 0. Because starting from this side, the non-negative integer should be come down. And from here, you have to do the inversion. That's what I told you, the shortcut for 2's complement, right? So 1, 0, 0. MSB is 1 here because since the number is negative, right? So in this way, we will follow minus 1 and minus 4 also. Here 0, for 0, all are zeros. This is the advantage in 2's complement, friends. In 2's complement representation, only 1 0 only is possible. Whereas in sign magnitude and 1's complement, there is a drawback about 2 zeros are coming, plus 0 and minus 0. Whereas in 2's complement, only 1 0 is coming. Fine? I hope you understand. Now next see. Positive numbers, for all positive numbers, only true binary form will be formed and MSB will be 0. Same as in 1's complement representation. Okay, the range in 2's complement representation is minus of 2 power n minus 1 to plus of 2 power n minus 1 minus 1. Here minus 1 won't be there. 2 power n minus 1 minus 1 won't be there. That minus will be in 1's complement and sign magnitude representation. The difference here is minus of 2 power n minus 1 to plus 2 power n minus 1 minus 1. Right, friends? Hope you understand. Please carefully understand this, use these examples and be careful in the value of ranges.